Okay, well, welcome everyone. So we are continuing our discussion of the boson-Hubbard model. So this is a bunch of bosons on really any lattice uh, in D space dimensions with a hopping element for each boson of W and a repulsion between the bosons of U on site. And then you vary the density by varying the chemical potential. And we described how you came up with this famous phase diagram, which has a bunch of lobes at each integer density where you have a mod insulator. And then the rest of the phase diagram out here, it's a superfluid. So in this region, you have a post condensate, B is not equal to 0. And in this region here, it's equal to 0, expectation value. All right. And what we started to do was to try to understand the nature of this phase transition between the insulator and the superfluid across this phase boundary. And we kind of argued that if you were looking at phase boundaries which involve changes in the density, then it really wasn't much to it. It was simply you adding a bunch of extra bosons in a background of the mod insulator and just maps onto the dilute post gas. But the most interesting thing that we now are going to focus on today and say much more about is the fixed density transition, which happens right at the lobe, at the tip of the lobe. And there's some line here where the density along this line is also n equals 1. So you're in a system at fixed density of n equals 1. And if you have strong interactions, you're in the mod insulator. If you have weak interaction, you're in the superfluid. And you'd like to understand how you go between them. Okay, so that's the context. Any questions? All right, so what we derived last time was a field theory for this, which is right here. Oops, this is not scanning. Oh, there we go. So the field theory has a path integral over some complex field, psi of x and t, which is controlled by a Lagrangian, as we call it, in imaginary time. This is a Lagrangian on D space and one-time dimension, and had the following terms. There was a potential, if you wish. So this last two terms don't depend on the gradients of psi. So you could call this V of psi is these terms in this row here. And this is the very familiar Landau-Ginzburg-like potential with a psi squared and psi to the fourth term. And if you were doing mean field theory, we would naturally conclude that the phase transition happens when this coefficient of psi squared changes sign. So meaning that when the coefficient is positive, you have a potential like this, where psi is at the center, and when it's negative, it has a minimum out here, and we go into the superfluid phase. So, okay. All right, so we are interested in that phase transition, but we are also interested in spatial temporal fluctuations. So we have to look at terms that depend on the gradients of psi, both in space and time. And then when we did this, just by thinking about the structure of the problem, we find that there's a variety of terms. In particular, there's when you can add a term which is first order in time, but you can't add one in first order in space because that would break inversion symmetry. This thing is invariant under time reversal because you can send psi to psi star under time reversal. So it doesn't break time reversal, but you can't have any term that's first order in spatial gradient, so it begins at grad psi squared, and then there's always a term of second derivative of psi. Now, in principle, I've given you enough tools to compute K1, K2, K3, and maybe that'll be a problem in the homework to compute some of those things. But we won't go through that here because it turns out what we need, we can actually deduce by some very general arguments. We won't need to know the specific values of K2 and K3 for our purposes. All right, so any questions on how we got to this field theory? All right, so today the first most important thing I want to show is that along this fixed density transition that I've focused attention on, as I go along this line at n equals 1, or indeed at n equals 2, or any integer n at which there's a phase transition, then along this line, k1 equals 0. So this is really the most important result today, well, among other things. But along this line, everywhere on this line, k1 equals 0. Well, sorry, right at the tip, I should say. And that's really the most important place where we are interested in it. Right at the phase transition, k1 is 0. And even actually a distance away from it to leading order. Okay, so how do we come to that conclusion? So, as I said, you could just do the calculation and verify it works. You could work very hard. I gave you the value of chi-naught, and so that's what gives you this phase boundary here. Similarly, you could compute k1 and then find that right at the tip, k1 is 0. Okay, but let me show you how that follows. It's a pretty neat argument. Okay, so the argument is based on gauge invariance. Now, the theory that we wrote down actually has what's called a global symmetry, that if I rotate B by some phase factor e to the I phi, and psi by the same factor on every side by e to the I phi, then nothing will change in the path integral or the theory. So if I go back to this theory here that we started with, I don't have to make any approximation. This is a property of this theory right here, where you got, everything, both fields B and psi, and all coupled together. And they're all coupled in a way that every psi star goes with the psi, and in L0, well, that depends on H0, which if you go back, I don't know where that's H0, that's probably the previous notes. We had H0 somewhere. Yeah, here's H0. Every B dagger goes with a psi. So you can rotate it by a common phase. However, yes? But what we want to look for is something more. We want to make that phase not just independent of time or even independent of space. For now, actually, we won't need the term. So which are the terms in this exact path integral that are not invariant if the phase rotation was dependent on space? Well, this term right here, this couples together different sites. So if I had a different phase rotation over here than here, then this wouldn't be invariant. And so there is no spatial gauge invariance to begin with. Okay, so how about if we can, in this path integral, we make the phase rotation a function of time? Well, if we make it a function of time, this is perfectly okay because these are all at the same time. And then how about in L0? Well, H0 you can easily check. You could also make the phase rotation a function of time. It wouldn't change anything. The only guilty party which has a problem with the time dependence is this term right here. So if I now rotate by some phase, which is a function of time, then if B goes to B times e to the I phi, where phi is a function of tau, and you just plug this in here, then you will find that B dagger dB d tau will pick up a term. We'll go to, well, itself, there'll be one term which is exactly as before, but there'll be another term which will be I d phi d tau times n, where n is B dagger B, of course. Let me write it out. So there'll be an extra term which will not allow you to make this transformation. So that is not a symmetry or an invariance of this path integral. However, let's consider a more general problem. This seems like we are going beyond the scope of what you're allowed to do. But we're going to consider a more general theory in which this is a symmetry. So what we're doing is we're taking a global symmetry and we're gauging it. And at some point later in this course, we might discuss what we're doing here is really analogous to what's associated with the 't Hooft anomalies in field theories. This is a very baby version of it, so it doesn't deserve any fancy word for it, but we're going to see this argument over again in many other contexts also. Okay, so we're going to gauge this local symmetry. And for this to be a gauge symmetry, what we have to do then is we have to have another term which cancels this thing. You have to have something that cancels this. Well, what we notice is that this B dagger B appears somewhere else in the Hamiltonian. It appears in H0, multiplying the chemical potential. So yeah, here there's a minus mu times B dagger B. So if you make mu also time dependent and also not constant under gauge transformation, and if you're familiar with gauge invariance, what we're going to think of mu as the time component of a vector potential. So you can then check if I do this gauge transformation with phi time dependent like this, and both for B and psi, then I can ensure everything is fine, provided I also allow mu to be time dependent. Okay, so that would be the theory that I would be interested in. All right, but that's not the theory I'm working in. So why is this of any use to me? Well, the argument is that what I'm doing in this theory is I'm computing everything as a function of mu in some low frequency approximation. So this couplings K1, K2, everything that you see here, everything inside is a function of mu. So, and it's some strange function of mu that I don't really know. So I would expect if the variation in mu was also very slow in time to this order in derivatives, since I have all the terms here, they should remain the same function of a slowly time-dependent mu. So basically, what I want to then argue is that this theory written here, at least for small phi dot, should still be invariant under a small time-dependent mu. Okay. So then I look at what are the simplest consequences of a time-dependent mu. Well, it turns out the two terms I want to focus on are just these two terms here. Okay. So now what happens to this term under a gauge transformation? Well, that term, we know what that does. That just goes, that's K1 psi star d psi d tau. Well, that just goes to K1 psi squared d phi d tau under the gauge transformation. Okay, so now that's got to cancel with something else in this new theory. And what can it cancel against? And I don't understand this little circle that I'm seeing that you're not seeing. Sorry about this. Okay. Yeah, okay, what does it have to cancel again? Well, it's got to be canceling something that multiplies psi squared. So what is the term that multiplies psi squared? Oh gosh, this thing is crashing on me. Let's see. Sorry. Something's going on. I'm going to have to stop the share and do it again. Sorry about that. Okay, share screen. I think no, maybe it was a problem with not with the sharing, but with the. Okay, no, it's not the sharing issue. It's the notability issue. Let's try that again. Okay, all right. Sorry about that. So, which is the term that's going to cancel against this? Well, it's got to come from something that involves psi squared. So if I look at this action, where is psi squared? Well, there's a psi squared term here. And what depends on mu here? Well, the only thing that depends on mu here is this combination, or chi naught. Okay. So therefore, and that combination I'm going to call, yeah, okay, we'll just call that R, right? We're going to call that R pretty soon. So this thing here, I'm going to call R. So when I transform it under mu for a small change d phi d tau, so then this term R will go. What will R go to? Well, R will change as dr d mu if I expand to first order in phi, and then mu has a change which is d phi d tau. And there's probably an I over there. That comes from this transformation over here. So from this change in mu, I will get a change in R. And now these two have to cancel. And if you work out the signs carefully, the answer turns out to be, this gives you a value of K1. So K1 is equal to, written here more explicitly, minus dr d mu. So that's kind of a exact identity that must be satisfied. If you want to maintain this, if you want to see how this global, if you're allowed to take your global symmetry and extend it slightly to a gauge symmetry for slowly varying gauge transformation. This is a necessary condition. Okay, so it turns out you know that's a good thing to do, and you know it kind of makes sense that everything should be invariant under small. It should maintain its form under small slow time variations. If it didn't, it would mean that you know your whole system is unstable and you're starting from the very bad starting point where even slow variations change everything. So therefore, and also you can check, you do the calculation, this works out. Okay, so therefore we conclude that K1 is 0 when dr d mu is 0. Okay, now we go back to this picture. Where is dr d mu 0? Well, this line here is line of constant R, right? This line is, well, I told you K1 at that point, but everywhere along this line, all along this line, R equals 0. So as I change mu in the vertical axis here, R keeps changing. I change mu, R keeps changing. But at this point, we see that point is exactly the point where dr d mu is 0, just from the shape of the line. The tip of the lobe is exactly the point where dr d mu equals 0. Because just from geometry. And therefore, we conclude that since dr d mu is minus k, K1 is 0 there. So that's the proof. Cute. But what I haven't shown, which I will leave for you to read the notes, the notes that are under readings, is that the tip of the lobe is also exactly the point where the density is constant. That as you go through the tip, the density doesn't change. But it kind of makes sense because on this side you have hole-like excitations, on that side you have particle-like excitations. So right at the center is where you have both particles and holes, and therefore the density doesn't change. All right, so that's the basic argument that right at the tip of the lobe, the fixed density transition is described by this famous FiveFourth field theory. So it's a relativistic field theory now because you can see now space and time appear in a symmetric manner. I've even rescaled things to make the velocity of light, which is really the velocity of sound here, equal to 1. And then this is the Landau-Ginzburg type polynomial. So amazingly, in any dimension of bosons near the superfluid insulator transition on our lattice with integer filling, when you're going from a mod insulator to a superfluid, you have a relativistic field theory, emergent relativistic symmetry, and a relativistic field theory describing all the quantum fluctuations. So now at this point, of course, there's a huge amount of work on this type of field theory, and we're going to use some of that. But I'm not going to, I could spend the whole rest of the course just talking about this field theory. There's just a huge amount known. I'm just going to, in this lecture and a little bit of hopefully Now let's see how far I get this lecture. But this and the next lecture, we will just recall some basic aspects of this relativistic field theory. You know, some tools, basic tools that we're going to need in other contexts as we go along with the course. For us to say something physical, I mean, our purpose right now is to understand something about what's going on at this point. You know, so we have a simple physical picture, a wave in the superfluid. In the superfluid, we know that the boson condenses, and the lower energy excitations are just phonons or Goldstone bosons, whose energy vanishes as momentum goes to zero. Over here, we have a gap, and the gap above the gap, there are particles and holes that move around. What's going on here? What is the nature of the spectrum here? Well, it's still today not fully understood. In fact, in 2 dimensions, this becomes a strongly interacting conformal field theory. And you could say that the course by Daniel Jeffries right now is studying you know, some general structure of what happens at this point in a very different language. Okay. All right. So that's the main result that we've established. You know, I think, you know, okay, there were a few steps I skipped, but really nothing was put under the rug. We've shown you how near the superfluid insulator boundary, you have this relativistic field theory to worry about. And then that will tell you something about a new type of quantum system that we haven't met so far, which is something that's at the really in neither phase and has some very strong interactions at very long distances at the boundary between a superfluid and an insulator.
Sorry,
yes,
I might have just missed that, but like we fixed this like translation time this time phase, we canceled it, but there was also an issue with this term that couples different points in space. So how do we resolve that?
Oh, yeah.
That one?
All right. So that's what gives you the gradient size squared term. Okay. So what happened was, so so it's a matter of, I can try to show you a little bit how that's done. So this term here.
Right.
Okay. So I think the way to do this is first go to momentum space. So let me first show you what let's get another page here. Right. So in the original term, in the original lattice, we had, use another color. Yeah. So we had some on I and J, B dagger I, W I J, B J. Okay. Well, I should really, Wij is some matrix. It's a Hermitian matrix that depends on I minus J is equal to W of I minus J. So this means that when you take a Fourier transform, you can write this as sum on K, B dagger K, BK times W of K. Where W of K, well, if you ask what it is, just the Fourier transform is a sum on J of W of I minus J times e to the I K dot Ri minus Rj. All right, so if you just look at the sum, and you just expand this for small, let's imagine it's only nearest neighbors. Okay, oops. Let's expand this for small k. Okay, well, yeah, let's just do this for nearest neighbors. So for nearest neighbors, this will become sum over all directions, sum over alpha equals x, y, z. Then you get minus 2w times 1 minus cosine k, I believe, k alpha. Okay. All right, so that's what W of K is, and if as K goes to 0, this will be the first term is just minus ZW, and then the other term would be 1 minus, you sum over all of them, well, Okay, there's no, sorry, minus ZW plus, I believe, plus basically W times K squared, the vector K squared, plus order K to the fourth, just expanding the, okay. So that's the small k expansion of W of K. Okay, now if you go through the Hubbard-Stratonovich transformation, after the Hubbard-Stratonovich transformation, you will get sum on K psi of K times 1 over W of K times psi of K. So the Hubbard-Stratonovich transformation is the simplest in momentum space. It's just totally diagonal. And now I insert this answer in here. So at small k, this will be sum on K times psi star of K. And now you see the 1 over ZW, which I claimed without proof earlier, minus 1 over ZW. And then you get some correction, which will be, well, it better be plus, what is it? Okay, I can't do this in my head. You pull out a 1 over ZW, no, well, it'll be something like W over Z squared, something like that, K squared times psi K. And now you undo the Fourier transform. And so this is the same as integral d dx of minus 1 over ZW psi squared plus some coefficient I probably didn't get right, W over Z squared grad psi squared. Okay, so this minus 1 over ZW psi squared at long momenta gave me, yeah, so those two terms give me in this action here. Now this term here, okay, I got the sign wrong, and this term here. So I've shown you what the value of K3 is anyway. So it just comes from that. Getting K2 is a bit harder at K1. You have to do an actual calculation with H0. This is simple. Okay, other questions? Okay, so yes.
Yeah, along the like n equals 1, n equals 2 lines in the superfluid region, would there be superfluid flow or conduction, or would there not be? If you're
Yes, they
exactly
would.
on the line.
I mean, exactly on the red line here? It's on this line?
No, on the purple line.
Oh, over here.
The dark purple line.
This one. Oh, I'm
Yeah,
sorry. You're
yeah.
right. I was going about insulin. Yes, absolutely. There would be everywhere. There's superflow everywhere here. I mean, there's a lattice, but still, there's impurities don't do anything, or even lattices do anything to superflow. They can still flow no problem. Certainly, if these were charged boson, there would be a supercurrent and a Meissner effect and all of that. Yeah.
Even though the lattice would be completely filled.
Well, U is becoming very small, so it's not as if it's filled. I mean, there are lots. So it's certainly true that what happens in the superfluid is there are lots and lots of number fluctuations. So the picture you should have is that have I drawn the lattice anywhere? Okay, no. Okay, I'll go to the last page. Yeah, so the picture you should have is that, here's your lattice. Oops. So in the Mott insulator, they are rigidly fixed. But in the superfluid, the number of bosons is fixed. But there's lots of number fluctuations on each side. So, maybe this will have 2 of them, this will have an empty, maybe this may have 3, that'll have 1, and so on, so that the average density remains 1. But there's lots of number fluctuations. So the superfluid state looks like this. Right, I mean, one other way to think about it is the ground state of a superfluid, you said was, B dagger at K equals 0 to the power n on the vacuum. But now I can also write this as sum on I b dagger I on every site to the power n acting on 0. So now if we expand this thing out, this has got lots and lots of term. It has got nth power of one site and fifth power of the second site, so that all of them add up to n. Everything is allowed in this expansion here. But the density is still 1, right? If the number of sites is equal to the number of bosons, the density is still 1.
Yeah, thank you.
And the density on the average is also, on every site, the average density is 1, but on each site, the difference between the mod insulate and the superfluid, even though the average density is 1 everywhere, on every site, if you were to sit at a given site, you will see lots of number fluctuations, whereas here you wouldn't. So I think atomic physicists have different words for this. There's some kind of number squeezing. Yeah, here the number is squeezed, here the phase is squeezed, something like that. Number and phase are canonically conjugate. Yeah.
Okay, thank you.
Sure. Okay. All right, so then I believe the rest of this lecture, yes, will be more about this field theory. So here I've written out a very general field theory, which appears in many books, including my own, on what's called the FiveFourth field theory. And it appears in many different contexts in physics. So what I'm going to do, I think, the remainder of the time today is show you a few other contexts where it appears. And in the section tomorrow, you will see a more explicit derivation of one of those contexts. Okay. Right. So what we have this. So here's a field theory that I would like to understand. So I think of the field theory as a path integral in space and time, and I'm going to work all for now anyway in imaginary time. One of the important things we have to learn, and the reason I'm going through this, is to understand how we go from imaginary time to real time, and get something that will tell me something about my Bose-Hubbard model. But for now, let's just think of this as a field theory in imaginary time. On every point in space-time, there's a field phi, which has n components. Okay, n real components. So there's sometimes called the ON model because it has a large symmetry of rotations in n-dimensional space. And the Lagrangian is the Lagrangian we've already met. Of course, there's the polynomial, and it's conventional to put this factor of 4 factorial here for when you're dealing with FiveFourth field theory. We didn't have it for the complex case that we dealt with. And mu here goes from 1 to capital D, and I'll always use capital D to represent D plus 1. So capital D is space-time dimensions, D is space dimension, at least when we're dealing with a quantum system. Okay, so that's the relativistic FiveFourth field theory with n component fields. There's an implied summation over alpha, and here this is, phi alpha squared with sum over alpha inside, and then the whole thing squared. Only then do you have the right symmetry. Okay, so this is FiveFourth field theory with n components in capital D dimensions. And what we know is that this field theory describes a phase transition in almost all cases as a function of n and d, and there's some idea of universality, which was actually, this was the context in which universality was first understood by Kardenoff and Wilson, that many systems, even though they may be very different in the microscopics, once you get near a phase transition, then for many systems, not all, for many systems, the low energy theory is just described by this model. And so you can just work out things with this model. Only thing you need to figure out for your favorite system is what are the values of R and U, and then you have predictions for anything you want for long wavelength and low energy physics. Okay, and of course, this, as I said, this has a variety of systems. The case we have met so far is the n equals 2 case, because then you could just take these two component fields and write it as a complex field, and then you'll see it's exactly the same. Okay, so the n equals 2 case describes the superfluid insulator transition at integer filling in a little d dimensional lattice. That's how we met this theory. Okay, but there's another very important case where we now think of as a model not in d space dimension, little d space dimensions, but as a model in capital D space dimensions. So all dimensions become space-like. And then it describes the thermal phase transition of what's called the n-vector model on a capital D dimensional lattice. So now space and time, in a sense, are both sitting on a lattice, or it's just space. And so here's a lattice model that I can write down. On every point of the lattice, I have a vector, n component vector, ni. And then the coupling is just the simplest possible. I'm doing statistical mechanics at finite temperature. There's a factor of 1 over T here, which I've removed because temperature has a very different role in quantum mechanics, and I want to stick to that. So there's a T that up. If you're doing statistical mechanics, you would say K is some coupling, and T is the temperature. And I put temperature equal to 1. But equally, really, when I say K, I just mean K over T. Okay, just to brevity of notation. All right, so this model, you can just take a d-dimensional lattice and put in n vectors on each side with unit length, and then this is an ordinary integral on each side, and this gives you the partition function. So this is a very famous model. Of course, the most famous example of this is n equals 1. That's the Ising model, where n can be plus or minus 1. Sigma now becomes plus or minus 1. So this is the Ising model in capital D space dimensions. What about n equals 3? Well, n equals 3 is really actually the very first case where such models were concerned or historically considered. That describes a ferromagnet. So if I have an iron and I heat it up, then above a certain temperature, iron will become paramagnetic. And that happens at what's called the Curie transition. If I assume spin orbit coupling is small in iron, which it is, then you just get this very simple S dot S coupling. You can think of N as the local ferromagnetic moment in some region, which you put on a lattice. And then that describes this model. Okay, that's the way Curie talked about it. You may have also seen, and certainly when I see StatMech, I discussed this. If you do the van der Waals theory of a liquid gas critical point, it has great similarities to the Ising model. And the liquid gas endpoint is in fact described by the Ising critical point. And then all of these models for their respective values of N and D at long wavelengths map onto this model. It's all back to this. Okay, so these were historically the first contexts where such models were considered. You can also take a spin model or a magnetic model with spin orbit coupling so that the spins like to lie in a plane or along a given axis, and those would correspond to n equals 2 and 1. Okay, so let's just take this model on its own terms for a minute. Something you would learn in StatMech. What are the two phases of this model? Well, if you go to very high temperatures or small k, I should really write k here, then then the correlations of n's would decay exponentially. So yeah, before I go to that, so how do you go from this model to this model? Well, the general argument is that, okay, you have, and here I'm summarizing, of course, some insight that took many years to develop, but once it's there, I can just say it. It's relatively simple. You have these unit vectors on each side of the lattice. And then what you do is some kind of coarse graining transformation. You take your average over the value of n in some region. So you define phi alpha of x, which is a vector. Let me draw a vector. at X, which is something like sum on I near X. You have some averaging volume of Ni. Okay, you take some region here. This is the point X, and in this region there are lots of little vectors pointing in all different directions. And you just define some. You assume everything is important is long wavelength, and then you just define some average of phi in this region, and you do that in different regions, and then you couple them together, and you just write down some very general low energy Lagrangian that could describe the thermal fluctuations, and you'll end up with this. Okay, that's the very quick way. If you want to work a little harder, you do exactly what we did to the Bose gas. You do a Hubbard-Stratonovich transformation of this by a n vector field, and then you do a gradient expansion, exactly like I just answered in I think the question I showed you how to do the gradient expansion after the Hubbard-Stratonovich transformation. If you do all of that, you'll be back to the same thing. Okay, so I've skipped a lot of steps, but in the end, that's the reason this n vector model gives you also the FiveFourth field theory. Okay, so if you're now taking the language of the FiveFourth field theory, then at high temperatures, these decay exponentially, where C is called the correlation length. And for low temperatures, you'll have long range order, sort of like a Bose condensate. Whereas X goes to infinity, this correlation function, say for alpha and beta along the one direction, gives you a non-zero moment. So this is the analog of the Bose condensate. N naught is the ferromagnetic moment. Okay, so I went through a lot of materials there. So that was very quick. If you have questions, this would be a good time to ask. I guess I just want to give you a flavor of how this argument works, and really the intermediate steps that I skipped over are just precisely the analog of the steps we have gone through for the quantum phase transition, but even in a simpler context where we don't even have to worry about time. Questions? Okay, great. And so another thing so this will be covered in section tomorrow. So far I talked about classical models and in capital D space dimensions, which also map on the FiveFourth field theory at finite temperature. Now, if you're back to zero temperature and talking about quantum models, the simplest quantum model is the n equals 1 case. So what we have met is the n equals 2 case, but the n equals 1 case will also play a very important role in things we'll talk about even in the next chapter. And that's sometimes called the Ising model in a transverse field. So now you have a little d dimensional lattice. So this is now in d dimensions, not capital D. And you have a coupling between nearest neighbors, which, well, okay. If you were to look at my notes from my book, you would write this as sigma zi, sigma zj. So this normally would be written as sigma zi, sigma zj. But one of the most important contributions of quantum information theory is they've introduced a better notation. And so now we call them capital Zi, capital Zj. So these are Pauli operators or Pauli matrices acting on a spin. So on each side of the lattice, there's a quantum spin, which let's take in the Z basis can either point up or down. And what the first term says is, as in the Ising model, that they like to point in the same direction. That when they point in the same direction, because of this minus sign, you lower the energy. But this is a quantum mechanics, so you can get quantum mechanics by having a coupling pointing in the x direction. So this term on its own would say the spin should point horizontally when G is very large. So this is called the transverse field. This is the ferromagnetic exchange. And you can realize this model also in the laboratory. You can realize it actually with cobalt spins and in some compounds. where this is literally a magnetic field that you apply in a certain direction along the crystalline axis. There are other realizations, including in Michel Lukin's lab, but that's not literally quantum spins. It's in the same universality class as this model. Okay, so this model, Hai-Yu will say much more about tomorrow. In particular, what Hai-Yu will show you, how you start from this Hamiltonian and write it as a Feynman path integral and end up with, again, our favorite theory, which is the FiveFourth field theory here. Okay. Okay, so but let's just, for now, just see some very simple things, which you can just see by just staring at this. So suppose G is very small. Well, G is very small, I can ignore this term. Then what's the ground state? Well, every spin likes to point up or down. So there's a twofold degenerate ground state, all spins up or all spins down. And that's the ferromagnet, obviously. All the spins are either up or down. And that's the long-range ferromagnet. And depending on whether you pick this state or that state, this is a very simple example of a case where you've broken the symmetry. It's a discrete symmetry now. Wasn't a phase rotation symmetry. It's just spin flip symmetry. More precisely, go away. You can easily see that if you have a unitary operation U, in which you send Z to minus Z and X to X. And what is that operation? Well, that's very simple. You just rotate the spin by 180 degrees about the x-axis. So we just do a rotation of the spin 180 degrees about the x-axis. Then that will send Z to minus Z and Y to minus Y and X to X. Now, we don't care about Y because it doesn't appear in the Hamiltonian. But if both Z's go to minus Z, it doesn't change the Hamiltonian. And this, of course, doesn't change because X doesn't change. So there's what's called a Z2 symmetry, because there's just one operation whose square is 1, and that's the group Z2. And this operation, represented by this unitary transformation U, takes Z to minus Z and X to X. So this, when you pick this ground state or that ground state, these states are not invariant. Under this symmetry, this will go to that state, and this state will go to this state. So they're not invariant. And so the system always picks one, and that's the broken symmetry. What's a discrete symmetry? But of course, as we have already learned, if you want to really characterize a broken symmetry in some well-defined way, which doesn't depend on which one you happen to pick for whatever reason, you have to look at 2-point correlation functions, Zi, Zj. So for both these states, it's the case that if I take Zi here and Zj on the moon, that they're either both up or both down. So the plus product is always 1. And so this will just give me 1. And now the claim is that even when G is not very, very small, even when G, there are some fluctuations of the spin between up and down, on the average, there'll be a regime where they're going to remember their fluctuation. And so for this will be not 0. And as long as this is not 0, you have broken the symmetry. And this is completely analogous to the Bose gas. In fact, it's a simpler case. All right, so that's for very small G. There's a broken discrete symmetry, which gives you characterize this ferromagnetic moment. Conversely, what about for very large small G? Well, then you could forget this term, and this is the term that matters. And what is the ground state of that? Well, you just take the spin and point it in the X direction, where by the X direction, I mean the linear combination of up and down, as you know from your Pauli matrix algebra. So the spin is a coherent superposition of up and down. Each state is separately in up and down, and that's the ground state. Of course, please keep in mind that this state is not the same as this state plus this state. If you take this state plus this state and take a superposition of those two, that's what's called a Schrodinger cat state. This is a live cat that's a dead cat. You just add them up. Well, that's an allowed state. but it's not something very likely to occur because the environment will always pick one or the other. And that really requires coherence to create a Schrodinger cat state of the whole system. And the Schrodinger cat state in this language breaks the symmetry. Really, the correct state is one or this, and it picks one direction. On the other hand, if I take this state, wait, I write this here, and then I expand it out, that has two terms, which are just like the Schrodinger cat. There's one term where all are up, and there's one term where all are down. But that's a very, very, the total number of terms when you expand this out is 2 to the n, where n is the number of sites. So that's billions and billions of terms. Just two of them form a Schrodinger cat. But the actual state in this up-down basis is the sum of all of them. But why would you want to use that up-down basis? Because this is the right-left basis is the correct one, and it's a very simple state. It's just so another way to say this in a model language is this state and this state have no real entanglement between sites. They're just product states, as is this one. So in both limits, G much smaller than 1 and G much greater than 1, there is no entanglement. In fact, the place where there's the most complex entanglement is right at the critical point. And that's part of the reason why then we are interested in describing the field of critical point, and that leads us to this field theory. So yes, so if you look at the same correlation function that had long range order, which went to non-zero as I minus j went to infinity, now this obviously goes to 0 because it's just 0 once I is not equal to j. So more generally, you expect some exponential decay. And because this decays exponentially and goes to 0 as I minus j go to infinity, the Z2 symmetry is preserved. All right. So really, I've gone very quickly through this Ising model and transverse field and done very similar type of arguments that we could have also made for the Bose-Hubbard model, except this is even simpler because I don't have to worry about phases and things like that. It's just two states, up, down, and a Z2 symmetry. So what are the excitations of this Ising model? Well, the excitations are, so let's take G much bigger than 1 first, where the ground state was just product of spins pointing in the right direction. Well, to create an excitation, perhaps one of them will flip and point to the left direction, but any one of them could have flipped. So what's going to happen is, as before, this thing is going to hop from side to side. So this will hop here and hop here. And so that hopping reverse spin will become a quasi-particle. So here there's no quasi-hole. There's only a particle. There's no anti-particle of this particle. And that's related to the fact that we're dealing with the real Z2 symmetry. So the field is real. This particle is kind of its own anti-particle, even though it does become relativistic near the critical point. And this flip spin can hop around, and that has a gap, and that's the particle when G is much bigger than 1. Oops. And when G is smaller than 1, well, then the ground state, let's say in 2 dimension, was all spin pointing up. Well, occasionally there'll be a quantum fluctuation where there'll be some bubble of spins pointing down, and this bubble will move around. And so there's some, here it's more complicated. You have these bubbles moving around, and that forms another particle. Okay. So actually, it might be useful to just think in terms of the FiveFourth field theory. If you accept the description of the FiveFourth field theory, then here you have this potential phi, and this fluctuation of phi around this point is the same as this little flip spin moving around, because it's fluctuating about phi equals 0. Phi is like sigma z or x of the z operator. Whereas here you're in the broken phase. Now phi is real, so there is no Mexican hat, but you have some region. Basically, it's like a solitron where most of the region, in the green region, phi is over here, and in the purple region, phi is over. Phi is over there. Right. So the most of the space is here, and then there's a little bubble where it jumps over to the other side, and that kind of so the fluctuation here and back, that whole object is what constitutes the excitation of this. Okay. All right. And finally, let me finish this lecture by mentioning yet another model, a quantum model, which is described by the n equals 3. We've met n equals 1, it's the Ising model transverse field. We've met n equals 2, which is the Bose-Hubbard model at the superfluid insulator transition. What is n equals 3? Well, one example of n equals 3, and this has been also studied in a lot of experiments, is sometimes called a coupled ladder antiferromagnet. So what is this? Okay, so here's the actual model. So you have let's say a square lattice of sites. On each square lattice in the experiment, there's a copper atom. Copper atom turns out to be, under the right condition, have exactly one unpaired electron. So each site has a spin, electron spin, which can point in any direction, just fluctuating. And these spins are coupled to each other. And because of the nature of the coupling between copper spins, which you can learn about in 295p, you find that the coupling is this exchange interaction, Heisenberg exchange interaction as it's called, is fully rotationally invariant. And that's important for the n equals 3 physics, which is, say, between site C and D, it's SC.SD. Okay, so now if I make all the couplings the same, well, that's the square lattice antiferromagnet, but to get a quantum phase transition, I have to do something else. So imagine I get a system, and there do exist that system in the lab, where you can make crystals like this, where on the purple lines, the coupling is K, and on the red lines, the coupling is J. And, and this S.S is, of course, XX plus YY plus ZZ. And suppose I am also able in the lab to tune the coupling K over J. Actually, there's even ultra cold atomic experiments where they built this kind of thing, I think in Emmanuel Bloch's lab. Maybe even Marcus Greiner. Somebody can correct me. All right, so suppose I could tune K over J. So let's ask what happens. The simplest limit is when K goes to infinity. If K goes to infinity, I just ignore all the red lines and I only look at the purple lines. Whenever I look at the purple line, the system just splits into dimers, to pairs of spin coupled to each other. Now I know the ground state of that. The ground state is each pair of spin will form a singlet with its partner, to be up down minus down up, and that's the ground state. Okay, so that state is completely rotation invariant. Everything is a singlet. On the other hand, when K equals J, well, that's the square lattice model. And for that model, it's known that the spins actually polarize and form what's called this nail state, where half of them are up and the other half are down. So this would be the ground state, will be something like up, down, up, down, up, down on this checkerboard pattern. Okay, and you can read about, I guess, yeah, it's not really in the readings, but we won't need this very much. But it turns out that as you vary the ratio K over J, I'm just giving this to you for information, there's a quantum phase transition from the nail state to the dimer state. And this phase transition is again described by this n equals 3, our favorite FiveFourth field theory. All right, so I've given you many different physical systems. I mean, really, this is like a history of the biggest hits in statistical mechanics over the past century. This FiveFourth field theory describes, the liquid gas critical point, the Curie transition in the ferromagnet, the superfluid insulator transition, of quantum transition, the quantum transition in the transverse field in an Ising model, where it's between this state which is like a Schrodinger cat to one thing that's really not a just locally pointing superposition, the local coherence but no global coherence of the spins of that in that sense. And then also this thing where you form spins forming singlets, or spin polarizing in this case, is also described by this field theory. Okay, so the next lecture we'll then go back to this field theory and just look at it a little bit more. Yeah, actually, it may take all of next lecture to do a reasonably honest job, and where it will allow us to say a little bit more about what's happening near the critical point. And in some sense, the rest of the course is really about other systems, other phases, and other critical points of quantum systems, which are not described by the FiveFourth field theory. The FiveFourth field theory is almost too successful. It seems to be perfectly okay in the vast majority of cases, but we are learning there are many, many other, more and more expanding library of materials and systems where you can't fall back to this FiveFourth field theory, and that's really what the rest of the course is about. But first, let's meet and fully understand the case that's very well understood, which is this field theory. Okay. Any more questions? All right. Well, so tomorrow there's a discussion at 9 and a section at 4, right? Where in section you will discuss the connection between this model right here, and the FiveFourth field theory with one component. All right. So,
excuse me.
Yes,
excuse
question,
me.
please.
Subir.
Yeah.
I think
yes, Joanne.
in the past I post on chat. I think they are only ignored, but today I think I need to speak up. So I post on the chat. It's in the chat. I just mention whether the description mostly chat. The chat is in the chat.
No, I have to figure out. I should learn how to see the chat when I'm sharing my screen.
That's a tricky part. Yes. Whether this.
Okay, I'll stop share. Then I can see the chat. Yes. Okay, go ahead. Now I can see the chat. Oh, so you're asking about ON or SON?
Right. Except maybe the Z2 case, the ON is probably crucial. Otherwise, I just wonder whether there's some importance for ON.
Okay. So if you, once you get to the FiveFourth field theory, there's really no difference. I mean, the FiveFourth field theory does have an ON symmetry. Okay. So let's just say we're talking about ON. Now we go beyond the FiveFourth field theory, and you're considering various topological terms and other things that we will talk about. Yeah, then the difference can be important. But for now, it's not important. Yeah, let me just say. So if you want, for definiteness, let's just say I'm talking about ON, if that's what you want. No, for now.
Sure. Okay. Thanks.
Yeah. So basically, phi goes to minus phi is a symmetry. You can change the sign of any number of components of phi and not change anything without change. But in some cases, in some physical applications, if you really think about it, sometimes when you do an inversion in phi, you also have to do a time reversal, but not at the level of the ON model, of the phi field theory, and of the terms that we retained. Okay, actually, sometimes the lattice, in some lattices with strange symmetries, you have to worry about this, but that affects the irrelevant terms, and we are not talking about those here. Yeah, so then it depends in detail on what system you're looking at. Sometimes it can make a difference to which irrelevant terms are allowed.
Thanks.
Sure. Other questions? Okay, so I should also say that if you look on the website, of course, under lectures, they are precisely the notes that you're seeing when I share the screen. But there's more detailed discussion, especially on this chapter when I'm taking a slight diversion to talk about just FiveFourth field theory, just teaching a little bit about field theory on its own. there are more detailed notes of that with more complete derivations in under readings. Look at the folder called readings, and there I've copied about 3 or 4 chapters from my book and put it over there. And of course, there's many other books. I think the book by Mehran Kardar also has statistical physics, has a lot of discussion of the FiveFourth field theory, but I think almost all in the context of just classical phase transition at finite temperature. Whereas our focus will not be on those. Our focus here, of course, will be on the quantum low temperature properties near a quantum transition. Yeah.
Subir, I have a naive question.
Yes, please.
Can the cat state you mentioned, like the superposition of all ups and all down, be the ground state of the transverse field Ising model?
Yes, it can. I mean, sure. It is. If you take a perfect, suppose I took the transverse field Ising model. Let me share it again. Yeah, so if I take this model, it'll depend whether I get the cat state or not. It will depend precisely on the boundary conditions. Suppose I take this model and put it on a torus with periodic boundary conditions, then I believe the cat state will be the ground state in a certain regime. It'll be a state which is, this plus this. That'll be the ground state, but exponentially close to it. Exponential meaning e to the minus n, where n is the system size. I should say, let's say e to the minus L, where L is the system size. There'll be another state with this minus this. Okay. No, but in any real system, you're not on a torus. You're always coupled to something on the boundary. There's a few stray cosmic rays hitting you or whatever, and those will, in general, pick out, invariably either up, not the cat state, but all up or all down.
Then in principle, like any superposition between the all up states and the all down states can all be the ground states, right?
Yeah, I mean, so what will happen if you put the thing on a torus? Like I said, it depends a bit on, exactly the type of boundary condition, but in principle, you can take, on a torus, you'll get a ground state, which will be all up, all up, plus all down, if you wish. But there'll be another state just nearby, which will be the same thing with the minus sign. And this energy splitting will be basically e to the minus L, where L is the system size. It's very, very tiny. So that's why, because of this very tiny energy splitting, e to the minus 10 to the 23 is is a very small number. So any weak perturbation will just destroy, whether it's plus or minus. It'll give you some other very complicated state. And typically, since you're measuring the perturbations are acting locally, they will destroy this coherence, which requires, long range order across the entire sample. So you'll just collapse effectively into up or down. And the other states, there'd be other excited states where, say, one spin is down. So this is an excited state. And this gap is finite. This will be of order J or K or whatever the couplings were.
Okay, thanks.
Sure. All right, great. So see you on tomorrow, 9 o'clock, or if not, on Wednesday. Okay.
Thank you.